Alright, so now let's look at applying a system of inequalities to a more applications-focused type of problem. Alpine Products produces air conditioners and fans. The air conditioners require 3.2 hours of assembly, while each fan requires 1.8 hours of assembly. The factory can operate for a maximum of 144 hours per week, and we'd like to sketch a graph of the feasible region for the system of inequalities that describes this situation. So let's see. We need to come up with some sort of equation or inequality that describes the fans and the air conditioners and how much time it takes to manufacture these air conditioners and commercial fans. So we're going to need to introduce some variables. Two different things that are changing here are how many air conditioners and how many fans we're producing. So I'm going to let x1 be the number of air conditioners, and I'm going to here we go, and I'm going to let x2 be the number of fans. The first thing to do when approaching this type of problem is define your variables. You can't start anything until your variables are defined. Let's also see what we know from the problem. Okay, so air conditioners require 3.2 hours of assembly and a fan requires 1.8, and we know that there's a maximum of 144 hours of assembly that we can use in a week. So let's write an inequality that describes how much assembly time we're using in 1 week. So let's see. The air conditioners are going to contribute 3.2 hours for each air conditioner. So if I take 3.2 and multiply it by x1, that gives me the total number of time spent producing air conditioners. And that combined with the amount of time spent making fans, that will be our total amount of hours spent on assembly each week. This has to be no bigger than 144 because our factory is limited to 144 hours per week. Now this inequality right here is something that we could find a solution for on its own, but we have two more conditions. Since we're actually talking about a physical thing, the number of air conditioners produced can't be any smaller than 0. And the same is true for the number of fans. I can't produce -2 fans. So we have these added conditions that x1 must be greater than or equal to 0, and x2 must also be greater than or equal to 0. It is possible that we produce no fans and no air conditioners, but it would be impossible to produce negative fans or negative air conditioners. So this would be our system of inequalities. So now we'd like to graph the feasible region for this system of inequalities. I'm going to let my x1 be the horizontal axis and the x2 will be the vertical axis. So we're going to graph, let's see, so I said x1 will be horizontal and x2 will be vertical. And just like I've done in the past, I'm going to find my x and y intercept for the line so that I can graph it easily. So let's see, if x1 is equal to 0, then we have 1.8 x2 equals 144, and so x2 is going to be 144 divided by 1.8, and that should come out to 45. So we have 1 point at 0, 45, so 0, 45. And let's see, our second point, if x2 is equal to 0, then we'll have 3.2 times x1 equals 144. And so x1 would be 144 divided by 3.2, and that should be 80. So we'll end up with a second point at 80, 0. So let's see, here's 80. So we have 2 points, and we want to connect these with a straight line. We can connect these with a solid line because the inequality is less than or equal to. So we'll pretend that goes through 80. Okay. All right. Let's see. Now we also have x1 is greater than or equal to 0 and x2 is greater than or equal to 0. X1 was the horizontal axis, so if x1 is going to be greater than or equal to 0, then that would be our vertical axis, and greater than or equal to 0 means we're pointing towards the right. Anything on the right hand side of this line will have x1 greater than or equal to 0. Let's see, x2 greater than or equal to 0, so this would create a horizontal line. And our x2 values, those were the vertical axis, so if we need those to be greater than or equal to 0, then our region is going to be pointing upwards. And so now we just need to figure out which side of the diagonal blue line, which side of the 3.2x1 plus 1.8x2 less than or equal to 144, which side will give us a solution. So let's test a point. I'm going to try the origin because it's not on my blue line for sure, and it's easy to plug in 0. So let's see, 0 plus 0 less than or equal to 144. That is true. 0 is less than or equal to 144. So that means that our solution set will point towards the origin. So the origin is here at 0, 0, so we have to be pointing towards the origin. So our overlap then is going to be this triangular region filled in right here between the vertical axis, the horizontal axis, and our diagonal blue line. Okay? And so that would be our feasible region for the given scenario. This is what we call a bounded feasible region because it's completely enclosed, but it would be possible to have an unbounded feasible region as well.